Today your beauty is going to interact with beauty of physics, because beauty of physics lies in symmetry, and solid sphere is a really very symmetric object, and you are going to study about potential due to a solid sphere having some charge. So let's get started. So now I am going to only write the expressions for potential and field due to a spherical non-conducting solid sphere having some charge. I am not going to derive it. It's your homework to derive it. You are going to simply replace capital G with K and mass with charge, and you will be able to derive it. It's really very easy. I am not going to derive it. For your practice you should derive it, and I am going to write the expressions. So for a point outside, inside, and on the surface, field and potential, intensity of field actually. So outside it will be equals to kq by r square, where k is the constant, q is charge on the sphere, and small r is the distance of the point from the center of the sphere. For a point inside, for a point on the surface, it will be equal to kq by capital R square, because small r will be equals to capital R, and for a point inside it will be equals to kq by 2r cube whole into 3r square minus small r square, and its potential will be kq by r. Actually the sign in front of this depends upon the charge. If the charge is negative, it will have a negative sign. If the charge is positive, it will be positive. Whatever it is, all our convention that which sign we put in front of the term. So here it will be equal to kq r by r cube, and this will be equals to kq by capital R. So now we are going to plot graph for it. So now I am going to draw the graph for potential due to gravitational and electrostatic forces. So first let's draw it for gravitational force, and next we will draw it for electrostatic force. For gravitational force, potential is negative and it has the maximum value at the center, because on the surface it is 3/2 times of that on the surface, and outside the sphere the potential decreases exponentially. The potential is actually inversely proportional to r square, means it will decrease. So let us assume this is the point where the potential is maximum, means at the center, and for point on the surface it will have the value k cube gm by capital R square, and for the point in at the center it will look something like, let me write the expression first. For inside point it is gm by 2r cube into 3r square minus small r square, right? So inside it will decrease with the increase in distance and has the maximum value at the points of center. If I put small r equals to 0, then it will look something like 3 gm by 2r, right? For center it is 3/2 gm by r. For this point it is gm by capital R square, and for point outside it decreases, and outside it looks something like gm by small r square with a negative sign, because potential due to gravitational force is negative, means force is attracting. And for electrostatic, the graph will be the mirror image having the mirror parallel to x-axis, means it will just flip. I have to just replace it with 3 by 2 k cube by r. Sorry, by mistake I have written it square of it here. It is actually minus gm by r, because I am drawing graph of potential. I am by mistake I have written the value of gravitational field intensity. I am sorry for it. You just raise the square down and add gm by capital R and minus gm by small r. So here on the surface it will be k cube by r and will decrease k cube by r outside the sphere, and for point inside it is gm by k cube by k cube by 2r cube 3r square minus r square. So actually this looks a little bit clumsy. I guess you have understood it. You can write it down yourself. My work was to make you understand the graph, and it is done now. Let me erase this thing and draw the graph due to field. Inside the solid sphere, value of gravitational field is gm by 2 r cube into small r. And if small r is 0, means at center the value will be equals to 0, means this point. And as we increase the distance from center, it will increase till it reaches the value of that at surface, and at surface small r will be replaced with capital R and the value will be gm by capital R square. And outside the surface it is gm by small r square minus means it will decrease being inversely proportional to r square. Actually I am talking about magnitude will increase, as there is a negative sign, means it will have a means the value will increase, but magnitude, I am talking about magnitude. Here you have to ignore the sign, because sign actually indicates the nature of the force, being attractive or repulsive. And for the electrostatic, obviously once again the mirror image, and it will look something like k cube by r square, k cube by small r square, inside it is k cube capital R cube into small r, right? So now we are going to derive the equation for potential and field due to a solid disk. Now consider a circular disk AB. We are going to calculate potential at a distance small r at point P, center be O. To calculate the potential, we are going to actually divide the circular disk into infinite number of rings, means something like this. We call this elemental ring because this is an element of this circular disk. Let us call this ring CD. So now let us suppose this this actually makes an angle of alpha with point P, and let us suppose this ring makes an angle theta. So first actually we are going to calculate the field due to this elemental ring, then we will integrate the infinite number of rings to get the total field due to this circular disc. So here I can write that theta is here, tan theta is, yes, let us suppose here the radius of the ring be x and its thickness be dx. From this you can say that here you know that circular disc looks something like a 2D object because it has length and breadth, means 2 dimension, and its thickness is really very negligible. That's why it's not considered as a 3D object. We can say that something like a aluminium foil. So here we are also going to discuss about surface charge density, because we are considering the charge to be distributed upon the the mass to be distributed throughout its surface, not the volume, because the third dimension means the thickness is negligible. So here we are going to consider sigma, surface mass density. So now we are going to calculate the mass, because to calculate the gravitational potential mass is required. So here the mass will be its area into sigma. Its area equal to 2 pi x into its thickness, because its perimeter into this thickness will give its area. You can also suppose cut this ring and open it, then you will see that it has a thickness of dx and its length is equal to its perimeter, that is 2 pi x. So now its mass will be equal to, let us suppose this is to be dm equals to 2 pi x dx sigma. So now actually if I take this small element of this ring and this small element of this ring, it will have the field looks, let me draw it here so that things will be clearly visible. Yes, now if I consider this element and this element, here is the point, I will have the field due to both of these elements. It is inward, it is also inward, means attracting towards itself. Now I am going to break it into components. It will have two components, a vertical, a horizontal. It will also have a vertical and horizontal component, but as the mass is equal, distance is equal, and therefore this value will be equal to this value, but both of are in opposite direction, so this value will cancel out, and these two values are in the same direction, that is attracting towards itself, and that's why it will add up. And here the angle is theta, as I have written here. It means that the cos component, we know that this if this is the vector, the angle it makes, means the cos theta will have cos theta component will be along this line with which it makes the angle theta. I hope thing is clear. Let me repeat it once again, means this vector is making an angle theta with this line, means its cos component will be along this line, and here it is making an angle 90 minus theta obviously, so this will be the sine component. So now we know that the field will now what I have written here, the cos component of the field will add up and the sine component of the field will get cancelled out, means the vertical component will cancel out, the horizontal component will add up and we will get the value. So now what is the formula of field? it is Gm by r square. So we can write that potential due to this ring will be equals to, and this thing will happen for all of the element, means this will have a opposite element here, this will have here, and all the diametrically opposite, means opposite along the diameter will obviously cancel out this vertical component. It will look something like, now this component is getting cancelled out, this component will cancel out, this and this, but this component will obviously add up because every component along the horizontal direction will attract, not repel. That's why only this horizontal component will add up. And now we are going to calculate the potential. So what is the potential? Field will be equals to G dm by r square. Here the distance is Cp and this distance is equals to okay, the radius of this disc be capital R. And now let us suppose the distance to be y square, G dm by y square. So now we are going to calculate the potential and the field. So G dm here is 2 pi x dx, and we are going to use the sine theta, the cos theta, because sine component will cancel out, by y square. So now I can do something like, here x equals to this y cos theta, actually I was talking about tan theta, right? Tan theta will be equals to x by r, and now x will be equals to tan theta r. And now I can differentiate it, means I can say that dx equals to sec square theta r d theta. Actually I am going to differentiate this equation, x equals to tan theta r with respect to d theta. So if I differentiate this with respect to d theta, it will be dx by d theta, and this will be equal to sec square theta r, and therefore if I multiply its denominator with right hand side, means this cross multiplication, after cross multiplication I will get dx equals to tan theta r into d theta. So this is the expression I am going to find, and here I have taken y square. Let's do something about y square. Here I can say that y is equals to r by y equals to cos theta, means base by hypotenuse equals to cos theta. So y will be equals to r sec theta. So I am going to replace y with this with r sec theta and dx with sec square theta r d theta. So now I am going to find, sigma is missing here, 2 pi g into 2 pi x dx sigma. So let me erase this upper part so I can write here. Now I have the potential G 2 pi x. X can be replaced with r tan theta because x by r equals to tan theta. So r tan theta and g into mass into dx equals to r x square theta d theta by the distance, that is r square x square theta. So here I can cancel x square theta r, and now I am left with 2 pi tan theta sigma d theta. This is the field, total field, but we are going to take the cos component, means the horizontal component. So I am going to multiply this with a cos theta. Tan theta and cos theta will give us sin theta. So now we are left with g2 pi sin theta d theta. So this is the field due to intensity of field due to a elemental ring, but we are going to calculate it for the total circular disc. So I am going to integrate it. The angle was increasing from 0 to alpha. So the field will be equals to integration of this having the limit 0 to alpha. g2 pi sin theta d theta. These things are constant, we will get out of the integration, and integrating sin theta we will get minus of cos theta, minus of cos theta, minus of putting the limits we will get minus of cos alpha and minus cos 0, means plus cos 0, means cos 0 minus cos alpha. So cos 0 is 1, so we will get 1 minus cos alpha. So it will be equal to g2 pi 1 minus cos alpha. So actually this I have missed a sigma. Yes, g2 pi sigma is missing here. Here this 2 pi 1 minus cos alpha is the solid angle subtended by a cone. So I can call this the solid angle omega, and this will be equal to sigma g omega. Minus negative sign, I have forgot about negative sign. So this is the thing, and if I consider the circular dish to be infinitely big, means something like a infinite sheet. So imagine a building in front of you. You generally look at this angle, means 0 degree. When there is a very high building, then your eyes go like, oh, where is the top of the building? You will like this, and finally you will be able to see the top of the building. Here, when turning from this point to this point, your eye makes an angle 90 degree. Just like if this plate is infinite, this point will make let me erase, sorry, I can write also here. This is making an if this is the height of the sheet, then it will make angle this. If I increase it to this, angle will increase till its the angle becomes perpendicular to this plane, means becomes 90 degree. For infinite plane, alpha will be equals to 90 degree, cos alpha equals to cos 90 degree equals to 0. So this will be equal to sigma g 2 pi. So this is for today. Actually, you know about this expression sigma by epsilon naught in electrostatics for electric field due to a what we call electric field due to a infinite plane containing some charge distributed on its surface. It looks something similar to that of the electrostatics, and actually it is a better way to study both of the topics because they have a lot of similarity. So you know that for conservative field, negative gradient of potential is field, and for the potential you have to integrate the field with dr, means dv equals to edr, and after integrating it you will be able to find the potential. So here we have minus g sigma omega as field, multiplying it with the dr, integrating dr we will get here e looks something like constant. Integrating dr means the small distance. After integrating the small distance, we will get the total distance between the point and the point where mass is situated, and it will be equal to r, and finally potential will be equal to g sigma omega r. So this is for today. So in the next lecture we are going to talk about Gauss theorem. So Gauss law is actually used in mathematical physics to change the integration, the type of integration. We have a lot of Stokes law, Gauss law, Green's theorem, and all to change the type of integration, means to make a line integral to a volume integral to surface integral, and vice versa. So we will talk about the specific case in that of gravitation, in which how Gauss law makes the equation, not the equation, the problems get solved easily due to some symmetry and some calculations. So this is for today. Thank you.